Hello, George Romanic here. Today we are going to talk about self-diffusion. Perhaps one of the most important videos thus far on this channel. This concept is very simple to understand, but as you will see today, it is not that simple to quantify. And we had this same issue, so to speak, when we were talking about Reynolds transport theorem. Reynolds transport theorem says, if something comes in, something has to leave, or the amount of that something has to increase in the volume where something came in. If you understood what I just said, good. If not, go and watch my video on Reynolds transport theorem. In the case of self-diffusion, we have the following situation. Imagine gas in this room, air. And right here, where my arm is, imagine we somehow color these atoms or molecules of air. And then we let the nature do whatever it wants to do. What will happen? Well, what will happen that these colored atoms or molecules of air will start diffusing. And after a certain time, they will uniformly occupy the volume of my room. The concept is simple. Atoms of a gas will diffuse over time to uniformly occupy volume that is at their disposal. Very simple. Question: how do we quantify this? Not very simple. And that's what we are going to do in today's video. We will use the concepts of kinetic theory of gases. Today's video is one of the pinnacles of kinetic theory of gases, because everything that we learned so far will be applied to investigate and understand self-diffusion. So, let's start. Consider a very big box full of particles. Now, I will divide this box into 4 imaginary layers. So, this will be layer number 1. Here we will have layer number 2. And here we have layer number 3 and layer number 4. And imagine that the width of these layers is the same, despite the fact it might not be the case in my figure. Now, I will add 20 particles in each of these layers. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3. Further, this will be the z-axis, namely height. All these particles are identical. And what I will now do, I will add tracer particles to this box, and I will color them in red. These tracer particles are exactly the same as these, but somehow imagine we could paint them in red. So I will add 8 tracer particles in the layer 1. So 1, 2, 3, 4, 5, 6, 7, 8. So I added 8 tracer particles plus 0 black particles in addition to first 20. Here I will add 6 red particles. 1, 2, 3, 4, 5, 6. So I added 6 red particles, but to have the same number of particles everywhere, I have to add 2 more black particles here. So 1, 2. Consequently, I will add 4 red particles over here. 1, 2, 3, 4. So I added 4 red, but then I also have to add 4 black to be the same number of particles. 1, 2, 3, 4. And lastly, I will add 2 red particles here, and then I have to add 6 more black. So 6 more black. 1, 2, 3, 4, 5, 6, and 2 red. 1, 2. What we did here, as you can see, we made a situation where we have absolutely identical particles. Each layer has the same number of particles, but layer 1 has more tracer particles, namely red particles, than layer 2, which in turn has more of these particles than layer 3, and then that one has more than layer 4. So we created the gradient of tracer particles. Now let us say that capital NT is the total number of tracer particles, which clearly would be 20. 8 plus 6 plus 4 plus 2 is 20. We will define number density of tracer particles as n small nt, and that is, as always, number density is total number of particles divided by the volume of this box. And we call that number density. T stands for tracer. And you can see from this figure, that was the whole goal of figure, that nt is nt of z. It depends on height, z. Now imagine we set up this situation and we let time running. What will happen? Well, what will happen is that over time, these red tracer particles will mix. And after a certain period of time, there will be equilibrium, which means on average, there will be 5 red particles in each of these layers. Of course, we have to now also say that we are not allowed to add or remove any more particles. But for this equilibrium to be established, that means that more particles from layer 1 need to flow to lower levels compared to the number of particles that are flowing from these lower levels into layer 1 and 2. And now the question is, how do we quantify this? Well, this is where the fun really begins, because now we have to be mathematically rigorous. I will introduce an imaginary surface between layers 2 and 3, right here. So I introduce this imaginary surface that goes into the page and out of the page, like so. And I will take, so this is the surface element, and I will take a volume element somewhere here in the box. And now I will zoom in this figure over here. So what I'm saying is, imagine this over here is this surface element ds. And somewhere over here I will take a volume element, because I will use spherical coordinate system, will maybe look something like this. But really it can be volume of any given shape. I'm just deciding to make my life easier, so I'll take a volume element that maybe looks like this. I will introduce spherical coordinate system, which means, as you can see, this is my z-axis, this over here is my y-axis, and this over here will be my x-axis. This surface element will have unit area. ds is 1. Whatever that area is, I will call it unit area. Distance between the surface element and this volume element is r. In spherical coordinate system, this angle is theta. And as always, we have to project now this radial distance to the xy plane to get our angle phi, azimuthal angle phi. So this volume element dv has coordinates r, theta, phi in spherical coordinate system. This is easy. Now, the question is, how do we find the number of tracer particles, red particles, that are passing through this area ds in unit time? This is now a very important part of the video. First, we will find the average number of tracer particles undergoing collisions in this volume dv in unit time. Second, we will find the fraction of these tracer particles that after collision inside dv travel towards ds. And third, we will find the fraction of these particles that are traveling towards ds that will actually reach ds without colliding with some other particle on their way. To put this in a numerical form, let d and t, which is clearly now a function of this vector r, be the average number of tracer particles which collide in dv, leave in the direction of ds, and reach ds without another collision. Then this d and t of r will be equal what I just said. Total number of tracer particles that collide in this volume dv times fraction of these particles that is moving towards ds times fraction of these particles now that will eventually reach ds without colliding with some other particle. And this is what we will spend the rest of the video working on, because we need to find these three quantities. First, we will tackle nt dv. From my previous video, we defined collision frequency, you will remember, capital Z, between two particles to be average speed of atoms in the gas, v divided by lambda, where lambda is the mean free path. And this is collision frequency, which means that's average number of collisions per unit time. Mean free path, of course, is the average distance an atom travels before colliding with another atom. Well, if this is collision frequency between two particles, then Z times nt, which is function of Z, is collision frequency of nt of Z particles in unit volume and unit time. Because this quantity in my video on collision frequencies, you will remember, was derived for unit volume and unit time. Therefore, to get collision frequency not in unit volume, but in this volume dv, we multiply by dv. So Z times nt of Z times dv will be collision frequency of nt, which is function of Z particles, in the volume element dv in unit time. In other words, this is the average number of tracer particles undergoing collisions in this volume element dv in unit time. And that is this quantity that we are interested in, which means I can now write that d nt is equal nt of z times z times dv and times f1, f2. Let's put it in bracket because we will later deal with these. Now I can express nt of z using Taylor series, and that's what we are going to do on the next page. We saw that, but we know from my video on spherical coordinate system that the volume element in spherical coordinate system is the following. So we have average v divided by lambda nt of z, and this volume element, of course, is r squared sine theta dr d theta d phi. And furthermore, we will express this dependency of the density number of tracer particles with height z using Taylor series expansion. I will write that nt as a function of height is equal nt at height z equals 0. And just to go back to this graph, z equals 0 is here. And then I use Taylor series expansion to find the change in the concentration of these tracer particles as dependency on z. So plus delta nt delta z evaluated at z equals 0 times some z increment and plus higher order terms, but we will neglect higher order terms because we are assuming that these changes in concentration are not very abrupt. But this height z can again be expressed using the spherical coordinate system, because we know that z in spherical coordinate system is r cosine theta, which means that this will become nt at z equals 0 plus delta nt delta z evaluated at z equals 0, and instead of z I write r cosine theta, which means that this expression over here becomes nt dv is equal mean speed divided by mean free path r squared sine theta dr d theta d phi and times this, which is that. So times nt at 0 plus delta nt delta z evaluated at 0 times r cosine theta. Very well. So if we go back to our original equation, we found expression for nt dv. Now let us find this fraction f1, which is fraction of particles that after collisions will go towards ds. What do I mean by that? Well, if we have that volume element over here, and we just said there are collisions, and these collisions are random, but my surface element ds is over here. So what I want to know is how many of these particles will go towards ds, because these are the one I'm interested into. I don't care about these that are going in the opposite direction or some other direction. So this fraction, which we called f1, is clearly related to solid angle that this surface subtends over here on this, in this volume element dv. So we will say that the fraction of particles that leave dv in the direction of ds is solid angle subtended by this surface ds divided by the whole space, which is total solid angle. A nice analogy for this is, imagine you have a board, and here that board has area A, and here you have some smaller sub-area, small a. And now you are throwing darts randomly. And you ask yourself, what is the probability that I will hit region inside of small a? Well, that probability is small a over large A. If small a is large A, probability is 1, because that's logical. If A is 0, probability is 0. Well, this over here is exactly this concept, but extended to 3 dimensions. Extended to space rather than area. Well, going back to this, what I just said is F1 is the solid angle subtended by ds, I will call it d omega, divided by total solid angle, well, that's 4 pi. But from my video on solid angle, I explicitly derived that this d omega is equal ds times cosine theta divided by this radial distance, which is r squared. Of course, if you are not familiar with solid angle, you cannot conclude this, but that's why I spent entire video demonstrating this relationship. And I also said we have to use absolute bracket over here, because this needs to be positive, and solid angle could end up being negative when we look into the element dv that is in the negative part of the z-axis. And to prevent that, we have absolute value over here. At any rate, check my video on the solid angle if you want more details. So combining this information, I get that F1 is equal ds absolute cosine theta divided by this 4 pi times r squared. Going back to our original equation, you will notice that we now found this parameter and we found F1. The last thing that we need to find is F2. And what is F2? Well, F2 is saying, okay, we found particles that are after collision in dv moving towards ds, but some of them will collide with particles in this interval over here and they will never reach ds. So what is the fraction of particles that are traveling towards ds and that will actually reach ds without colliding with some particle? Well, to find that, we will use the concept of mean free path. Mean free path, again, lambda is the average distance a particle travels between collisions. And of course, we always assume that collisions are random in the gas, and that therefore 2 collisions are independent of each other. How do we find the probability that a particle that is leaving this volume element dv will actually reach ds without colliding? Let's assume that this line of sight is perhaps this. And let us assume that this distance over here, whatever it is lambda. On this path, let's take an infinitesimal increment dr. Probability, let's call it here small p. Probability of collision along this infinitesimal increment dr is clearly dr divided by lambda. Ratio of this to the mean free path. And once again, that follows from the same argument that I provided here with darts, but here instead of area we have lines, 1 dimension. So this is the probability of collision along dr. Just to convince you further, if dr is equal 0, well, this probability is equal 0 because particle didn't move, so it cannot collide. On the other hand, if dr is lambda, probability is 1 because lambda is average distance over which particles collide. Therefore, what is probability of no collision in this interval dr? and I will call that capital P. That is, of course, 1 minus small p. If p is probability of collision, then probability of no collision is 1 minus that probability. And we can see it is 1 minus dr over lambda. So how do we now combine an interval of arbitrary length r, which we had here, and dr? Well, let capital P of r be probability of no collision in the interval of length r, then probability capital P of no collision in the length interval r plus dr will be probability of no collision along r times probability of no collision along dr, but I calculated that here to be 1 minus dr over lambda. This can be confusing, of course, so I'll give my best to one more time explain what we got here. I think this part is quite simple. Now, how do we get probability of no collision in the interval of length r plus dr? Well, imagine this is some interval of length r, and probability of no collision along this interval is some capital P of r, whatever that is. Now I increase this length interval by this distance dr. So the total length is r plus dr. What I'm saying is, probability of no collision on this new interval is probability of no collision on this interval, which is capital PR, times probability of no collision on this small increment, but I just calculated here what is that probability. The last thing now that I perhaps need to convince you is that I'm multiplying these probabilities rather than summing them up. And that's because these are independent events. And that's because here at the beginning of this discussion, I told you that these collisions are random and independent. Two collisions are independent of each other, and that therefore probabilities of independent events multiply. And that's why we have multiplication over here rather than some other sign. Excellent. Now I will extend the left-hand side using Taylor series in the following way. Probability of r plus dr is equal probability at r plus dp dr times dr plus higher order terms, which I once again will neglect. These cancel, and I get that this probability can be written as probability of no collision along r plus dp, which is also a function of r. Now plugging this over here, we will get that p of r plus dp of r, where all these p's are capital P's, equals, I will multiply this, so that is p of r minus p of r dr over lambda. Notice that this and this cancels, and I get differential equation that separates variables. So dp dr is equal negative dr over lambda, where lambda is constant. So I can integrate this. When r is 0, probability of no collision is 1. And when we have some arbitrary distance r, then the probability of collision is some capital P. Of course, mathematicians would hate this. Oh, I see here, it's not dp over dr, but dp over p. Namely, differential equation that separates variable. I move this p over here, and then I get negative dr lambda here. Sorry, it ends up Professor Romanich doesn't know differential equations that separate variable. Anyways, upon this integration, we get here that ln p in the limits between 1 and p is equal negative r over lambda. Or I can write therefore that ln capital P minus ln 1 is equal negative r over lambda. But ln of 1 is 0, so we can see therefore that really p after passing with exponential function is equal e to negative r over lambda. And for those of you that love statistics, you will recognize that this is Poisson distribution. So we can see that probability of no collision along a distance r follows Poisson distribution, which means as the r is increasing, probability of no collision is decreasing. When r is 0, probability of no collision is 1. That perfectly makes sense. When r tends to infinity, 1 divided by infinity tends to 0, which means probability of no collision tends to 0. And that makes sense because as r is tending to infinity, eventually that particle will encounter some other particle and collide. And this is our factor f2 in this equation, which means that now we can combine expressions for ntdv, f1 and f2 and write the expression for dnt of r. And that's what I'm going to do on the next page. We started from this and now we found these three factors, so I can write that dnt as a function of r is equal. This first factor, you will remember, was average speed divided by the mean free path r squared sine theta dr d theta d phi times nt evaluated at 0 plus delta nt delta z evaluated at z equals 0 times r cosine theta, that's this nt dv term, times f1, and we found that f1 was ds cosine theta divided by r squared, that's f1, and times f2, which we found to be e to negative r over lambda. Now what we will do is analyze this expression by looking at the total number of tracer particles hitting this unit area ds. So as I said, ds is unit area, so I can here replace it as 1, in unit time from above and below. In other words, let's go here. As you can see, this ds was unit area. So let us now use that expression to see what is the number of these tracer particles hitting this unit area from above, namely from layers 1 and 2, compared to the number of red particles that are coming from below, from layers 3 and 4. To do that, I will introduce n plus to be total number of tracers hitting unit area from above in unit time. And from above is the key term here. And similarly, I will define n negative to be total number of tracers hitting the unit area from below in unit time. So what would be this n plus? Well, that would be, I have to integrate this long expression. So that would be integral from 0 to infinity. Now I'm covering all radial distances, dr. Then I have to integrate angle theta between 0 and pi over 2 d theta, and I have to integrate d phi from 0 to 2 pi. Let's go back to our figure to see why. Now when I'm integrating for this northern hemisphere, so to speak, and you can see that r can go from 0 all the way to infinity, theta can go from 0 to the y-axis, which is 0 to pi over 2, and I'm going around circle, which means that angle phi is going from 0 to 2 pi. And that is exactly what you see here in these limits. And then I have here, of course, the rest of this expression, which is, I forgot 4 pi over here. Nobody told me. Why didn't you tell me? Anyways, the rest of this expression becomes average v divided by, let's put 4 pi lambda. Notice that this r squared can cancel with this r squared. So I will just get sine theta dr d theta sorry, there is no dr, d theta, d phi. I move them here. You see, this is what happens when you're doing things live. And then I will have here this term, nt of 0 plus delta nt delta z evaluated at 0 times r cosine theta. I cancel this r square with that r square. ds is 1. So I will have here cosine theta. And I don't have to keep now absolute value because I'm here in the positive part of angle theta. So I can just remove absolute value. And finally, I have e to negative r over lambda. Very well. Now, what is n negative? Well, that is integral from 0 to infinity dr. Now theta is integrated from pi over 2 to pi. This is the difference because now we are going into the southern hemisphere over here, so to speak. So theta is going from here to the negative part of the z-axis, and that is from pi over 2 to pi d theta integral 0 to 2 pi d phi. And then again here I will have average v 4 pi lambda sine theta times nt of 0 plus delta nt delta z evaluated at 0 r cosine theta. Now this absolute cosine theta becomes negative cosine theta. I'll put here negative. So that becomes negative cosine theta. And because cosine of these angles between pi over 2 and pi is negative, and because of this absolute value that becomes negative cosine theta, e to negative r lambda. Excellent. Now, what we want to find when we define these quantities is the net transport of tracers in the negative z direction per unit time through this unit area. So, n plus minus n minus will be net transport So clearly what we need to do now is to subtract these two expressions, and that's what I will do on the next page. So now we have to do this calculation. N plus minus n minus is equal. We will have three integrals, integral dr, integral d theta, and integral d phi. R, of course, goes 0 to infinity. Theta goes 0 to pi over 2. And phi goes in circle 0 to 2 pi. And then we have first term associated with n plus, and that will be average v divided by 4 pi lambda, mean free path, and t of 0, sine theta, cosine theta, e to negative r over lambda. And then plus second term associated with n positive. So we will again have integral dr, integral d theta, and integral d phi. And again, they go from 0 to 2 pi, 0 to pi over 2, and 0 to infinity. Average v divided by 4 pi lambda. But now it's the second term associated with n plus, and that is delta nt, delta z, evaluated at z equals 0, r sine theta cosine squared theta, e to negative r over lambda. And then plus, I will have first term associated with n negative, and that will be again integral dr, integral d theta, integral d phi. R, as always, goes from 0 to infinity. Here we have to be careful now. Theta, I'm going to the southern hemisphere in my figure, which means theta is going from pi over 2 to pi. And phi is again circling from 0 to 2 pi. And then we have this term over here. And finally, plus second term associated with n negative. Now the beauty is that the first term and the third term, when combined, will give me 0. So I can write something like this. These two give 0. Why is that the case? Well, this integral with respect to theta, sine theta, cosine theta, with the limits between 0 and pi over 2 is 1. And this integral, the same integral, but in the limits between pi over 2 and pi, is negative 1. So 1 minus 1 will end up being 0. That leaves us with the second term and the fourth term that contribute to this subtraction. Namely, n positive minus n negative will be equal integral 0 to infinity. I have to be careful here now to collect all terms properly. So I will have here r e to negative r over lambda dr. So that's everything related to r. Then I will have integral, now very important, from 0 to pi, I combine these two. So integral from 0 to pi, and with respect to theta, I have sine theta cosine squared theta d theta. And lastly, I have integral 0 to 2 pi d phi. There is nothing that is dependent on phi. And then I have times the constant, and that would be this. Average v divided by 4 pi lambda delta nt delta z evaluated at 0. Now this integral over here, I explicitly solved it in my video on the mean speed of atoms in a gas. I suggest you check out that video. It is solved using integration by parts, and the solution of this integral is lambda squared. This integral I will solve for you here below using my quick and dirty method. And of course, this integral over here is simply just 2 pi. This integral using quick and dirty method becomes integral 0 to pi cosine squared theta, and sine theta I will say that is derivative of negative cosine theta, so I have to put negative here. And now this becomes table integral, so this is negative cosine to power 3 theta divided by 3 in the limits between 0 and pi. We know that cosine of pi is equal, what is cosine of pi? Negative 1, and cosine of 0 is equal 1. So that means this integral further becomes negative. So we will have negative 1 to power 3 divided by 3 minus positive 1 to power 3 divided by 3. And that is equal minus 1 times minus 1 is positive 1 times 1 more minus 1 is negative 1. So that will be negative, and then I will have minus 1 over 3 minus 1 over 3, and that is equal 1, because this minus will make these minuses positive, so I will get 2/3. Which means I can write now that n positive minus n negative is equal lambda squared, that's the first integral. Second integral I just calculated it to be 2 over 3 times. This integral is 2 pi times this constant average v divided by 4 pi lambda delta nt delta z evaluated at 0. Notice that this squared and this lambda will cancel. 2 times 2 is 4, will cancel with this 4. Pi and pi will further cancel. And we will get that n positive minus n negative is equal mean speed of atoms times mean free path of atoms divided by 3, this 3, times delta nt delta z evaluated at 0. Very, very important result, and effectively the end of our derivation. Notice that if delta nt delta z evaluated at 0 is positive, that means that n plus minus n minus is also positive. But what is that telling us? Well, this being positive means that there are more tracer particles that are hitting our unit area from above than from underneath, which means there will be net transport from positive to negative z direction. And that is what we wanted to show, because we said if we have more red particles over here and fewer red particles over here, and here is my plane, here is my z-axis, I'm quickly replicating our original figure, that means if this is positive and this is positive here, then this will be positive, and that means overall there will be flux of red particles from the high concentration region into the low concentration region. This is so important result. Again, something very intuitive, but you see, it took a lot of mathematics and rigorous derivation to get to this point. Now, allow me to finalize this derivation by introducing a quantity jd of z that will denote the number of tracer particles crossing a unit area at z in unit time in the positive z direction. And this quantity is basically known as the flux of particles or the particle current. So, based on this definition, jd of z is simply equal n negative minus n positive, and that will be our previous result just with the negative sign because I reversed that equation. So I will have average v times lambda divided by 3 times delta n t delta z. And now this is not evaluated at z equals 0 as before because I am defining this quantity for an arbitrary plane at some height z. And this is known, as I said, as particle flux or particle current. Extremely important quantity is this over here, namely d, that's what we call d, coefficient of self-diffusion is equal average v times lambda divided by 3. Finally, we managed, after a long video, to derive our coefficient of self-diffusion. You can see that the units are meter squared per second in the SI system. And now we can say that particle flux in the z direction is really equal negative d delta nt delta z. Result we are all familiar with from literature, but in many cases, particularly in introductory courses, they state this, but now you know how to derive it. Of course, there is nothing special about z direction, so the same principle applies for the x direction, so this will be negative d delta nt delta x, and of course the same will apply in the y direction. jd as a function of y is equal negative d delta nt delta y, given that concentrations are changing in the z, x and y directions. Or one can combine these three expressions to get that jd as a vector, as a function of some r that combines x, y, and z, is equal negative d nabla nt. And this is known as Fick's law of diffusion. Of course, nabla is defined as delta x in the I direction plus delta y in the j direction plus delta z in the k direction, where I, j, and k are unit vectors in Cartesian coordinates. Check my video on Cartesian coordinates, so this is differential vector operator. This law, this great law, was first proposed by Adolf Fick in 1855, and it was based on experimental observations. Adolf Eugen Fick was a German mathematician that worked in this field, and he was a physicist and mathematician, but after actually discovery of these laws, he decided to move away from physics and he became a medical doctor and physiologist. At the very end, allow me to quickly examine this coefficient of self-diffusion d. You see here definition that d is average speed times mean free path divided by 3. From my separate videos, we know that mean speed of atoms in a gas is equal square root 8 k T divided by pi times m. When K is Boltzmann constant, T is absolute temperature, and m is mass of atoms. And free path, once again, I have separate video where I demonstrated, or rather derived, that lambda is equal KT divided by square root of 2. You remember we went into great lengths to demonstrate there is square root of 2 over here. Check that video. Pi times pressure times d squared, where P is, as I just said, pressure in the gas, and d is particle diameter. Now, if you take these expressions and you plug it in here, you will see that this d, coefficient of self-diffusion, is proportional to absolute temperature to the power 3 over 2 and inversely proportional to the pressure in the gas. What we demonstrate, therefore, is that diffusion is faster for both hotter and more rarefied gases. Also, you can see that smaller particles, smaller d, diffuse faster. And also, lighter particles that have smaller inertia will also diffuse faster. So, very, very important finding here. As per usual, I calculated coefficient of self-diffusion in meters squared per second for some typical gases that make up air that we breathe, and I also included radon for good measure. You will see that in all cases this coefficient of self-diffusion is order of magnitude 10 to power negative 5 meters squared per second. Furthermore, as you can see in one of the future videos, we will examine coefficient of viscosity. And you can check my previous videos to get proper understanding of all these other quantities: mean speed, mode speed, relative speed, mean free path, collision frequencies, and so on. Kinetic theory of gases shows you something your eyes will never see. Do not forget that. Let us now explore concept of self-diffusion using this beautiful online application. A link to this application is in the description below. Here we have a container that has this green divider. I will put, let's say, 50 particles in the left chamber of this container. These are blue particles. And I put 50 particles in the right chamber of the container, these red particles. We will look into particles' flow rate from left to right, namely how blue particles will invade the region of the red particles, and flow rate of red particles, how they will invade the region of blue particles once the divider is removed. So now let us remove the divider. Notice how the flux of blue particles is predominantly to the right and flux of red particles is predominantly to the left. As the time is progressing, we will have complete mixing of these two colors, and eventually the arrows will have the same length towards the right and towards the left. And you can already see that the length of these arrows is approximately the same. Of course, there are some fluctuations from one moment in time to the next moment in time, but on average, if you look at these arrows, they are the same length in both directions. And that means the system is in equilibrium. Why? Because of the concept of self-diffusion that we now discussed. Let us investigate what will happen if I again have 50 blue particles in the left chamber and 50 red particles, but I increase temperature of these blue particles to 500 kelvins and I decrease temperature of the red particles to 50 kelvins. When we remove the divider now, initially we will have higher flux of blue particles to the red. But as the time is progressing, the system will reach temperature equilibrium. And that means blue particles will give their energy to the red particles And red particles will, so to speak, slow down blue particles. So on average, blue and red will have the same speed. And that means that temperature is in equilibrium. System reached thermal equilibrium. Let's explore this. Notice how blue are inviting red, but as they are colliding, they are giving their energy to the red particles. Red particles are speeding up, blue particles are slowing down, and eventually we will have complete equilibrium. As you can see, as the time is progressing, once again, the arrows indicating particle flow rate to the left and to the right for both blue and red particles on average seem to be the same. Of course, from time to time that can differ, but on average they are the same, which means system reached thermal equilibrium. If we look into the center of mass of these particles, this is how it looks like, but it is oscillating somewhere around the middle of the container, which does make sense. This video presented the most complete derivation of self-diffusion using kinetic theory of gases on this platform, known as YouTube. On this channel, I never ask you to subscribe. I think you are intelligent enough to know whether or not you want to subscribe to my channel. However, I would like to ask you to share this video. When you go to Disco Club, talk about these videos with the girls that you meet there. When you print a gift card for your girlfriend or boyfriend, put the name of this channel so people are aware of these resources that maybe they want to learn about, but they just don't know that exists on YouTube. Post a link to my channel or these videos on your Facebook, your YouTube videos, except if you are a beauty blogger, then you don't have to do it. But LinkedIn, Instagram, and so on. That will help this channel grow. And people that are exposed to these videos, they are also intelligent enough to know whether or not they want to subscribe. Thank you. Until next video, goodbye.